Hello and welcome to another lecture session of Introduction to Astrophysical Fluids. In the last lecture session, I gave you a very superficial 0th level introduction to plasmas. Once again, this course is only to give you a very superficial introduction to plasma, and we will mostly be interested in the fluid aspect or the continuum aspect of a plasma. However, uh, in this lecture, we will also discuss some aspects, at least, just like we did it for neutral fluids, some aspects uh, of the different levels of dynamical theory. Okay, starting from the very particle description to the continuum description for a plasma. Okay. So we all know now roughly what a plasma is. So we start by just start this lecture by just characterizing formally a plasma. So we know that plasma is nothing but an ensemble or a collection of ions, electrons and neutrals. Okay, and plasma is in general obtained by heating or applying sufficient amount of energy to a gas. Okay, so plasma is called fourth state of matter, so this is an ionized gas. Okay, so this is the, of course, the definition of course, the practical definition of a plasma. But we have to be careful that any arbitrary ensemble of ions, electrons and neutrals, they are not a plasma. So we really need to specify the characteristics of a plasma, so that so that we do not just how to say, we do not just call any arbitrary ensemble as plasma, but to know that there is only a specific class of the ionized gas, they are called plasma. And how to characterize that? So we have several criteria. First one is that its physical dimension, which is capital L, should be very greater than the Debye length of the system. Okay, and this is known as the first plasma criterion, and that's completely very intuitively very well justified, because we already said that for a gas ensemble to be plasma, the first requirement is that the plasma, the ensemble should be quasi neutral, right? So it should have both, it should, first of all, it should have a global quasi neutrality. Okay, and also you can see that if we say this type of thing, that the physical dimension L is very greater than this lambda d, then we can also say that the charge neutrality is also achieved at the very local level. Okay, why is that? Because if you remember that lambda d is the length scale, okay, below which the charge neutrality cannot be expected, but beyond which the charge neutrality is always true. So if your plasma is like an ensemble like that, and you have several spheres with radius equal to Debye length, so just inside that sphere you can have violations in charge neutrality. But just if you take these spheres as the unit of your system, then your system will more or less behave as neutral particles. Okay, because you cannot see any charge neutrality, any violation to charge neutrality beyond this sphere. These spheres are known as Debye spheres. Okay, Debye spheres. And the thing is that if your Debye spheres are very small with respect to the global dimension of the plasma system, that means if they are like now this, then you can simply say that, okay, so almost locally, that means locally means like the length scale over which some plasma parameter can change considerably. So over that length scale, if you can expect the charge neutrality, then you can say that my system is locally also charge neutral. Okay, of course quasi neutral, as I said, that the charge density should be roughly zero. Okay, it should be negligibly small and not exactly equal to zero. Okay, I mean, if it is exactly equal to 0, that's something bonus, but in general, it is not really necessary. Now, the second criterion is the collective behavior, and that's very, very important for a plasma once again. Okay. And for a plasma, it is, I mean, the collective behavior of the particles are much more important than its individual behavior. Okay. So, and the requirement for this being true is that we should have enough number of particles in the device sphere. Okay. So, once again, so if your device spheres are consisting of one or two particles, then actually I mean that the charge neutralities are constituted only by one or two particles. And so if you are now seeing the system, you can actually say that, okay, the representative particle, which is a device sphere for this ionized medium, okay, is almost of the same scale of a real particle. So then individual particle behaviors cannot be neglected. But if your device sphere, every device sphere is consisting of a large number of particles, then you can say, okay, my the representative particle, the Debye particles, okay, of my ionized medium is much more greater, or consisting a very large number of the ions and electrons, so that the individual ions and electron properties are not really important always. Okay, of course, in explaining several phenomena, we need to use the information about the individual behavior of the particles, but we are not going into this. Okay, so this is something, once again, we are not saying that the individual behavior will be exactly zero or totally nullified. We are simply saying that the collective behavior is much important. Okay, and the requirement for this is that we have to have enough number of constituent ions, electrons inside the device sphere. Okay, and then we roughly define a parameter called plasma parameter in, well, this is roughly the number of the particles, okay, inside a device sphere. So the volume of the device sphere is this 4/3 pi lambda d cube, and n is the number density. So I mean, sometimes you can see this as a plasma parameter. In several books it is simply written in lambda d whole cube. Okay, that you can also write as plasma parameter, but whatever be this is just a matter of convention in both cases. So this one or this one should be very, very greater than 1. So that is the requirement, and this is called the second plasma criterion. Now the third one is also very true. So we just talked about the quasi neutrality in space. Now we talk about the quasi neutrality in time. That means the charge neutrality, if it is perturbed very weakly, okay, then of any species, then the corresponding species will try to respond in such a manner that the quasi neutrality is achieved or retrieved in a time which is equal to 1 by nu p. Nu p is nothing but the plasma frequency. Now omega p is called sometimes the plasma frequency in most literatures, but this is nothing but 2 pi times the real plasma frequency. This is the angular plasma frequency. Okay, so yeah, so 1 by nu p is the time, okay, to required for any species. So if it is TPI, that will be for the ions. If it is TPE, that will be for the electrons. It is the time required to get back or to retrieve the state of quasi-neutrality again in time. So an ionized gas to be plasma, the time scale of study of the system should be very, very large with respect to 1 by nu p. Okay, so that we never can see this this transient phenomena of the charge transient phenomena of the charge imbalance. So we always study the system in such a time scale that the charge imbalances are not really of importance. Okay, So that is the thing. But of course, there are several phenomena where charge imbalance, they cause something very important. Okay, so we were coming to that, but these are very rough primary criteria of a plasma. Okay, just you have a some static medium, ionized gas medium, and with respect to which now we have to conclude whether this gas medium is plasma or not. Then we use all these criteria. Finally, for weakly ionized gas, if the gas is not sufficiently ionized, that means the plasma is nearly a cold plasma, if you remember. Okay, then what happens? Then for this to be a plasma, the corresponding criteria is that the frequency of collision between the neutral and the electrons, because now the medium is consisting of a large number of neutral particles, that should be much less than the collision, I mean that the plasma frequency of the electrons. Okay, otherwise the charge neutrality would not be uh, preserved. Okay, so this is called the fourth criterion. Okay, so it is simply that if the charge neutrality is broken by a weak perturbation, and then after that if the collision between neutral and electrons, they are very frequent, then the particles are, I mean, do not find much reason to get back its original position of charge neutrality once again. Okay, and that's why then the once the charge neutrality is broken, it is very difficult to get back the charge neutrality again if your collision between the neutral particles and the electron is sufficiently large. Okay, and that is not what we want to get back the quasi neutrality. So this is the required criteria to get back the quasi neutrality. Okay, now how to describe a plasma in general? We already stated that plasma is the fourth state of matter, and so it has actually two components. One is the matter, another is the electromagnetic field. Okay, because the plasma is charged. Okay, so it has ions, electrons, and which are moving. So I said in the previous lecture that not only the charged electrons and ions and neutrals, but they should be moving. Okay, and as they're moving, then both electric fields and magnetic fields, they should be coming into play. Otherwise, you can also think of, so that is something they are creating. Now of course, if you give some external electric or magnetic field, okay, then also the charged particles will be affected by that. So when we are talking about the fields in a plasma, there are two parts. One is the fields, electromagnetic fields, which are exerted from exterior. Another is the electromagnetic field which are created by the species themselves. Okay, so that we will try to distinguish when we will talk about the equations, evolution equations of the plasma species. Okay, now just remember what was our previous objective: to make or to construct a dynamical theory for some for the continuum. For neutral fluid it was just the hydrodynamics. Now we have to make a dynamical theory for the plasma, so that we can do something for astrophysical fluids. Okay, and such a dynamical theory necessarily requires the evolution equation of both the matter fields and the electromagnetic fields. Now for electromagnetic fields we don't have much choices, right? We simply know that one is Maxwell's equation. So the field evolutions are they are always governed by the Maxwell's equation, so we don't have much choice there. So that is divergence of the electric field is equal to rho by epsilon 0, divergence of B is 0, curl of E is equal to minus del B del T. This is the Faraday's law, this is the Gauss's law. Okay, this is called Thomson's law sometimes. So simply it says that the magnetic monopoles does not exist. And finally, this is the Faraday-Ampere law, and which says that curl of B is equal to mu 0 J plus mu 0 epsilon 0 del E del T. This is the famous displacement current term, and E is the electric field, B is the magnetic field, J is the current term. Okay, rho is the charge density, J is the current density, mu 0 free space permeability, epsilon 0 free space permittivity. Okay, I hope all of you know about all these things. So this I am not going into this. Now for the matter field, we have several choices. Either we can write the single particle description like the normal like neutral molecules and kinetic, molecules or atoms, or any neutral particles. Then also, if the number of the particles is large, then we can talk about kinetic approach under certain conditions. Then we can talk about fluid description. In plasma exclusively, we have the provision of doing something a bit more special, and most people who are doing research sometimes, and they want to mostly do research in space plasmas or astrophysical plasmas, but they want to include the effect of particles interaction as well, or particle behavior as well. Sometimes they create hybrid models. That means they are interested in such a length scale or time scale, that so that the ions still, because ions don't move so much, so ions still behave as particles, and electrons, they behave as a fluid because they are very much mobile, so they can actually constitute a continuum. Okay, how is that? We will talk qualitatively in the next lecture. Okay, so we have several options. This one we will be not at all interested. This one we will start because first, even for the hydrodynamic case, we started from the kinetic theory, and from that we will just go to this, and then we will talk about the fluid models of plasma. A hybrid model, it is just for your own interest. Okay, if you are interested, you search about that. Now, in the scope of our course, we will mostly be interested in the fluid aspects of a plasma, but it is somehow interesting to discuss the different levels of dynamical theory for plasma. Okay, at least briefly the outline. So mostly the kinetic theory and the transition of the kinetic theory to continuum theory, or the theory of the plasma fluids. Okay. So now just remember that what I said, that a plasma needs to possess prominent collective properties, and then we realize that the necessity of a kinetic theory for a plasma can never be ignored. Okay, so sometimes it may seem that the kinetic theory of plasmas may be actually applicable to an ensemble of stars which are governed by inverse square laws, because both gravity field and Coulombic laws, Coulomb forces, they are both of inverse square laws. But remember, gravity field being attractive all the time, they cannot create any shielding effect, and that's why they cannot there is no characteristic length scale like Debye length scale beyond which you cannot see the gravity effect, the effect of the gravity effect is always there, so it cannot help in establishing a local or global thermal equilibrium. On the other hand, for the Coulombic forces, we have a shielding effect or screening effect, and so after a certain length scale, basically when you have a large number of particles, there is a screening effect, and after beyond that length scale, you cannot really find the effect of the Coulombic interaction, and there that's why finally the total system, after beyond the length scales, the total system actually governed by the thermal collisions, and thereby it is still thereby being able to establish a thermal equilibrium only for the Coulombic cases, and that is exactly the case of plasma. Okay, I end for this lecture at this point, and from the very next lecture I will start by developing very briefly the kinetic theory, and it's a very interesting aspect. It's called BBGKY hierarchy, and after that I will also introduce the corresponding from the kinetic equations, the transition to fluid models and magnetohydrodynamics. Okay, thank you very much.